Alright, in this video I'll be doing or going over the test 4 review, the first 2 pages here. And here it says determine the domain of the function. We've got f of x equals the square root of 3x plus 2. And if you think about the graph of f of x equals the square root of x, it looks like this. It's what I call the ET function. So your domain starts at x equals 0 and goes forever right. So it's 0 to infinity. That's your domain. The reason why is because I can't plug, now notice 0 is included in this set. I can plug in 0, the square root of 0 is 0, but I can't plug in any negative number. So basically whatever is under here, whatever I'm taking the square root of, has to be either equal to 0 or positive, because I can take the square root of a positive number. And so in doing a problem like this, I want my radicand to be greater or equal to 0. And by the way, that's the other way to write the domain here. I could say x is greater or equal to 0. Here it's my whole radicand is greater or equal to 0, so we need to solve this. We get 3x is greater or equal to negative 2. It's going to be x is greater or equal to negative 2/3. In interval notation, let me go ahead and graph this first. So greater or equal to 2/3, the graph would look like that. Those are the numbers that either equal negative 2/3 or are greater. And so in interval notation, that's negative 2/3 to infinity. Let's go to number 2. F of 4, well, we're just plugging 4 into this function. So we're going to replace the x there with 4. This is the square root of 8 minus 7, or the square root of 1, and so we're going to get 1. So when your output here is 4, your input is 4, your output will be 1. If you plug in negative 1, it's going to be the square root of 2 times negative 1 minus 7. We'll get the square root of negative 9. And we know we can't take the square root of a negative. This would be, well, it's something we haven't talked about yet, but it's an imaginary number. When we're dealing with functions, it's all real numbers. I always say we got to keep it real. So this is not a real number. Basically, what we're saying here is negative 1 is not part of the domain. If we were actually to find the domain here, like we did in number 1, we would see that negative 1 is not part of the domain. So we would just say not a real number here. F of 8, it's going to be 2 times 8 minus 7. It's going to be the square root of 16 minus 7, which is 9, and we'll get 3. And finally, if we plug in 10, we'll get the square root of 2 times 10 minus 7. Well, that's 20 minus 7. We're going to get the square root of 13. And notice there are no perfect square factors of 13. And I can't take the square root of 13. It's not a perfect square. So this is simplified. You don't need to change this. Let's go to number 3. Well, a couple of things. We learned that anything to the 1/2 power is a square root. And we learned if you had something like a to the 2/5 power, that would be a 5th root of a squared. And this too could actually go outside the whole radical. We could just put parentheses around the 5th root of a and put the square on the outside. But in any case, there's a saying that I have for fractions as exponents. And that's what we're talking about here when we say rational exponents. Here we have fractions as exponents. Fractions as exponents lead to radicals. We can write this in radical form. The denominator tells us the root of the radical. The 27 becomes our radicand. And now I can put the 2 here, or I can put it outside. Now I don't really want to square 27, so I'll put the 2 out here. And so the cube root of 27, we're looking for some number that you cube to get 27. That would be 3. Now, that's just this part. We're squaring that, and so we do get 9. Now, you could do this one in a similar way, but you do have the negative exponent to deal with, and normally that's going to be what you're going to want to do first. Is we know negative exponents lead to reciprocals. In fact, this is 1 over 32 to the positive 3/5 power. And so now we can do what we just did in part A. This is going to be a 5th root, since our denominator is 5, of 32. Now, I don't really want to cube 32, so again, I'm going to put my 3 on the outside here. Now, the 5th root of 32, we're actually looking for some number to the 5th power that gives you 32. Well, it's not 1. 1 to the 5th power would be 1. If you take 2 to the 5th power, that is 32. So this is just going to be 2. That's just the radical. Don't forget, we've got to cube whatever this is. So it's 2 cubed, and we get 1/8. It says use rational exponents to simplify. Write the answer in radical notation if possible. Well, we can write this as x to the 6/8 power. So we're changing to rational exponents. That's what it says to do first. But we can reduce this to x to the 3/4 power. And so now it says write in radical notation if possible the final answer. So this is a 4th root of x cubed. Again, this 3 could go outside or inside. If we're not dealing with numbers like we did in problem 3, then it really doesn't matter here. Let's move on to number 5. Now there's 2 ways that I showed you to do number 5. First of all, you could write this. This is probably the most common way, especially as you move up into higher level math courses. We're going to look for perfect squares in our radicand. Well, remember your perfect squares. You can see that 9 is a perfect square factor of 27, so that'll go here, and the leftover factors will go over here. X squared would be the largest perfect square factor of x cubed, and the extra x factor would go over here. Finally, y squared, that is a perfect square, and so that'll go there, and there's no leftover factor, and so we would get, let's see, the square root of 9 is 3, the square root of x squared is x, and the square root of y squared is y, and that's times the square root of 3x. Now the other way to do this is to prime factor it. Now 27 is 3 times 9, and 3 is prime, and 9 is 3 times 3, so we can factor this as 3 times 3 times 3. We've got 3 x factors and 2 y factors. So we talked about how if you're under the radical, you're in jail. In order to get out of jail, you need a pair. So we can pull out a 3. Notice we have a pair of x's, we can pull out an x. And we have a pair of y's, we can pull out a y. What's left over is 3 and x. Those get multiplied together. It's all multiplication, so whatever you pull out is multiplied, and so this is our final answer. You can get it either of those 2 ways. On number 6, the easiest way to do this is probably to write it as the cube root of 125 over the cube root of 216. Well, we know 125 is a perfect cube. It's 5 to the 3rd power. So if you're looking for something you cube that gives you 125, that would be 5. And here we're looking for something, a number that you cube to get 216. Well, if you check, this was 5 cubed. It turns out 6 cubed is 216, and so this is 6. All right, let's move on to the next page. Oh, let's adjust the camera here. So a couple of things, we talked about what we can and can't do with multiplication and division, as well as addition and subtraction. With multiplication, we learned that as long as you have the same root, and these are both square roots, you can multiply the numbers inside. If this was cube root and this was a cube root, you can multiply and this would be the cube root of AB. So as long as the roots are the same, you can multiply the numbers inside together and you keep the root. Similarly, if you do the square root of A divided by the square root of B, get the square root of A over B. So multiplication, division, as long as they're both the same root, you can do this type of multiplication or division. With addition and subtraction, we learned that it's not as easy as that. In other words, you couldn't add like a square root of 2 and a square root of 3 and get a square root of 5. You've got to have what we call like radicals. They have to have the same number under the radical, not just be both square roots. So if you look at 7a here, these are like radicals. And this would be 1 square root of 7, since it's understood there's one of those there. So this would be like adding 3x and 1x. You'd get 4x. In this case, you're going to get 4 square roots of 7. So like radicals are not only, they're both square roots, but they have the same number under the radical sign. The radicands are the same. Now notice this is not a like radical. All we can do is rewrite it separately. Now here at first glance it looks like you can't add these together because they don't have the same number under the radical. But if you remember your perfect squares, and so on here, you can see that this is not simplified. The square root of 50 is the square root of 25 times the square root of 2. You're going to get 5 square roots of 2. What about the square root of 18? Well, I'll do that over here. The square root of 18, well, 18 is divisible by 9, so this can be broken down into, or simplified to 3 square roots of 2. So notice what we have, 2 times 3 square roots of 2. Well, this is all multiplication. I can multiply the 2 with the 3, and I get 6 square roots of 2. And again, we can only multiply a square root of 2 times another square root, kind of like what we were talking about up here. Square root of 2 times square root of 3 would be square root of 6. But so we can't multiply that square root of 2 times the 6 because the 6 is not a square root. And so now we do have like radicals, and this is 11 square roots of 2. Number 8, we're multiplying using FOIL. We'll multiply the first terms. We know the square root of 6 times the square root of 6 is 6. Remember, really all we're doing here is we're squaring the square root of 6 and squaring a square root. These basically undo one another. You get just the 6. Square root of 6 times square root of 2, that's square root of 12. We can multiply the 6 and the 2. We were just talking about that here. And then your inner product is 5 square roots of 6. And your last product is 5 square roots of 2. Now you can see none of these look like they are like terms. Turns out they won't be, but you do have a square root of 12 here. Notice 4 is a factor of 12. So this can be written as the square root of 4 times the square root of 3. So we end up with 6 plus 2 square roots of 3 plus 5 square roots of 6 plus 5 square roots of 2. None of those are like radicals. I can't add a number with a radical, so we're done. Number 9, we're rationalizing the denominator. That means we don't want to divide by an irrational number. So to get rid of the square root of 7, or the square root symbol in the denominator, we can actually multiply the denominator by the square root of 7. Notice that'll get 7, and we got the radical out of the denominator. Of course, to make it legal, I have to multiply by the square root of 7 over the square root of 7, because that is 1. We can legally do that. We're not going to change the value. We end up with 4 square roots of 7 in the numerator. And again, this is done. We can't do anything else with this. You might be tempted to do something here, but I can only divide a square root by another square root. I can't do anything else here. On this one here, the first thing you're going to want to do is write it as the square root of 3 over the square root of 5. And now we can get the square root of 5 out of the denominator by multiplying by the square root of 5. And do the same to the numerator. You get square root of 15 over 5. Now again, it might be tempting to divide here. If this was the square root of 5, you would end up with the square root of 3. But you can't divide because they're not both radicals, not both square roots, and so we're done. Let's move on to number 10. So to get this radical out of the denominator is a little more complicated than what we're doing up here. You're going to have to multiply by what we call the conjugate of our denominator here. So whatever we do to the numerator or denominator, we do to the numerator. So again, what we're really doing is multiplying by the number 1. This is equal to 1, this fraction. We get 3 times 4 plus the square root of 11 over 4 minus the square root of 11 times 4 plus square root of 11. So here we're just distributing. We're going to get 12 plus 3 square roots of 11. And in the denominator, these are conjugates. The nice thing about it is notice the inner product and the outer product are going to be opposites, and so we don't really have to worry about those two products. We're just going to multiply the first terms, you get 16, and the last terms, a minus square root of 11 times a plus square root of 11, you're going to have a minus, and we know the square root of 11 times the square root of 11 is 11. So we get 12 plus 3 square roots of 11 over 5. All right, we're down to our last problem, which is actually 2 problems in one. So first of all, on number 11, we know that if we're solving a radical equation and there's only one radical, we want to get it by itself. You might be tempted to add these terms together, but you can't do that because one is not under the radical, the other one is. So what I know I can do is subtract 5 on both sides. We've been doing that kind of thing for a long time with equations. You get the square root of 3x minus 4 equals 6. Now that we've isolated the radical, we can square both sides. You get 3x minus 4 is equal to 36. We'll add 4 to both sides. We get 3x is equal to 40. So divide by 3, you'll get x equals 40/3. Now, normally I box it in after I check it. This does check. Let's go ahead and plug in 40/3. You can see here when you multiply, the 3's will cancel. You get 40 minus 4. This is the square root of 36. Well, that's 6 plus 5. That does equal 11, so it does check. All right, on part B, the main thing you need to see here is this is a cube root, and so the opposite of taking a cube root is not squaring, it's cubing. And so we're going to want to cube both sides. we're going to get x plus 5 is equal to negative 64. We'll subtract 5 on both sides. We get x is equal to negative 69. You can see that if you plug that in, the square root of negative, or cube root of negative 69 plus 5, that's the cube root of negative 4. I'm sorry, cube root of negative 64, and that does equal negative 4. So I do want to point out, if this had been a square root equal to a negative, we know we'd have no solution. But with cube roots or any odd roots, it is possible to get a negative. All right, so that's it for this video.